Kia ora tātea. Good morning, everyone. My name is Russell Gale, and I'm the Research and Development Manager for the Forest Growers Levy Trust, and I'm the CEO of Forest Growers Research. It's my pleasure to welcome you all to the 2020 Forest Growers Research Conference. Like many people today, we are having to do things differently from the way we have in the past. This year's conference was planned to be in Nelson, but due to the impact of COVID on finances and the uncertainty over travel and meeting venues, we made the decision to host this year's conference as a virtual event. This is the 14th Forest Growers Research Conference organised by Forest Growers Research and its predecessor, Future Forest Research Limited, since 2009. Initially, 2 meetings were held each year, but in 2013, this was reduced to 1 meeting a year. The purpose of this annual conference is to present the highlights of an extensive forest growing research program to our key stakeholders. It covers work funded by industry and government across the whole value chain, and it includes updates on work outside the FGR program. That is the radiata pine breeding, export log fumigation, and some updates from Scion on new wood products. The focus of the conference is on deliverables and outputs from the research work, and its importance to you as forest owners, with less emphasis on the detail of the research methodology. The speakers are all available to provide further details after the conference, and the presentations will be available on the FGR website. The Forest Growers Levy Trust is the body that oversees the Forest Growers Levy to ensure that levy funds are spent for the benefit of all forest growers. The levy was first introduced in late 2013 after a referendum of potential levy payers. At the end of the first 6-year term, levy payers voted overwhelmingly to continue it for a further 6-year term. The Forest Growers Levy Trust is a key supporter and funder of the research work we'll be presenting over the next 2.5 days. This year, its contribution to research is $5.4 million. This is around 60% of the Levy Trust's investment in the 2020 work program. The levy funding is extremely important as it enables us to access other government and industry funding, so that the total value of the research program is around $19 million per year. The next slide shows the Forest Growers Roadmap and the supporting science and innovation strategy. These guide the Trust's investments in research. It is the Trust's Forest Research Committee, comprising forest grower representatives from large and small growers, that guide the overall direction of the research program and make funding recommendations to the Trust. The next slide shows the research program funded by the Trust extends right across the value chain, from biotechnology developments, plant propagation, breeding, forest establishment and management, protection from fire and biosecurity threats, through to harvesting and supply chain management. In the case of the Specialty Wood Products Partnership, the program also includes investigating new wood product options for these species. Rather than structuring the presentations by research program this year, we have organised the presentations along the supply chain. This is to show where research interventions, guided by the priorities set out in the Science and Innovation Strategy, are being made to add value or improve efficiency, safety and sustainability of forest growing. While the topics being presented are of value to all forest growers, we have also added an afternoon session, repeated on Wednesday afternoon, that has an emphasis on practical tools and on other species that are often of more interest to small growers. We trust that you find the presentations that have been delivered and the Q&A after each session interesting and useful to you, and that demonstrates the breadth and value of the work being supported by the Levy Trust on your behalf. Many of you will be aware that I had been planning for a while to step back from the role of Research and Development Manager. I have been in this position since Forest Growers levy was introduced in 2014, and prior to that I was involved in the establishment of Future Forest Research that became Forest Growers Research in 2014. It's been a privilege to lead the Forest Growers investment in research and development over this time, and to reinforce the critical role that research and development plays in our industry. The industry we're all part of today has been built on previous research funded by the government and industry. Research will continue to play a pivotal role in the future as the industry responds to climate change, changes in society's attitudes and expectations, and biological threats and global market changes. I'm pleased to be able to hand over the baton to Bart Challis, who takes over the role this week from his previous role as Chief Operating Officer at Scion. He has a strong science and commercial background in biological sciences in Europe and North America, as well as here in New Zealand. I've got to know Bart pretty well over the last 2 years in his role at Scion, and I can say confidently that the industry are extremely fortunate in having someone of Bart's calibre coming into this important industry leadership position. Finally, a big thank you to those involved in putting this conference together. A special thanks to Veronica Bennett for her efforts in learning new IT skills, promoting the conference and pulling all the presentations together. A special thanks also to Alison Wilson and Kylie Gunn from Scion, who have coordinated the considerable Scion input to the conference. Also the session chairs and all of the presenters who have grasped the challenge of participating in this conference in uncertain times with enthusiasm and open arms. With that, I'd like to pass over to Bart Challis to introduce himself and make some observations on this new role before we start the first conference session on new wood product developments with an introduction by Sean McBride from J&L. Thank you.
Well, good morning, everyone. Obviously, it's great to be able to have a chance to introduce myself on my first week in the new role. As you can imagine, I'm pretty excited to have the opportunity to join the Forest Owners Association and really continue the work that Russell has been doing over the last 10 years or so in this role, and have the chance to continue where he's left off. You know, within the role, there's a great opportunity, I think, for forestry to innovate and you know, see huge potential in how I can hopefully help support that opportunity. So perhaps just a little bit of background about myself. I grew up here in Rotorua, and then moved on down to the University of Otago, where I spent a number of years and ultimately gained a PhD in genetics from the University of Otago. After completing my PhD, I did the classic Kiwi thing and spent some time overseas. Although in my case it was perhaps a little longer than most. I ended up around 16 years working across Europe and then North America, where I had a number of executive roles, but really my main focus was on the commercialization of science within the life science and biotech sector. And really what that enabled me to do was sort of leverage off my passion for translating science into value, rather than, you know, the purity of research. For me, it was always about how do you use the potential of creative thinking and innovation to generate tangible value, which I think aligns really well with the current role. I returned to New Zealand about 6 years ago, and most recently I've been working as the Chief Operating Officer at Scion. In that role, I've managed science operations and the delivery of science research across both the traditional manufacturing and bioproducts and also the forest sciences areas. So thanks again, and I'm looking forward to connecting with many of you in the coming period. Cheers.
Good morning and welcome to the 2020 Forest Growers Research Conference. My name is Sean McBride. I'm a Forest Manager for Dukin New Zealand Limited, based in the Wairarapa, and I'll be chairing today's first session, which is around new product opportunities to add value. Before I go into more detail about the contents of today's first session, however, I do want to recognise the efforts that the team at Forest Growers Research have made in organising the conference that we're attending over the next few days. The challenges that the COVID environment have brought are familiar to all of us, and this is no less than what the team at FGR have experienced in organising this. They recognise, however, the importance of disseminating the research findings to those of us in the wider industry, and I want to thank them for their efforts in making sure that that happens this year as well. I also want to recognise the work of Russell Dale, the Research and Development Manager for FGR, who is retiring at the end of this month. Russell's been a real advocate for forest research, and his passion has seen significant improvements in the research program over the last few years. I want to thank Russell for his efforts and wish him all the best in the future. So today's first session really has two streams to it. As we all know, the forest resource that we have for the next couple of decades is already in the ground and committed. So we have to look at ways that we can add value to the existing resource. The second stream is what other species can we look to further develop so that going forward we can add value through alternative species and the benefits that they bring. The first presentation today from Florian Greichen is around the options for higher value wood products. This will set the scene for a lot of the presentations that follow. The second presentation from Warren Grigsby, also from Scion, is around adding value to bark and biorefinery developments. I'm sure we can all appreciate the benefits to our industry if we were able to find an economic use for bark, which is really seen as a residue and not of much value to the forest industry, but the environmental and economic benefits of the potential biorefinery options need to be further explored. Following Warren, we have Rosie Sargent, also from Scion, and Rosie will be giving a number of presentations throughout this first session, the first of which focuses on thermal modification of Douglas fir and cypress. The ability to modify resource that we currently have in the ground is where thermal modification really comes into its own. The ability to add hardness or durability to current species means that they'll be able to be used in applications not historically used for them. Following this, a further presentation from Rosie around the peeling of Eucalyptus fastigata for laminated veneer lumber. I've seen a lot of the findings of this piece of research, and there's certainly enough evidence in the results of this research to pique the interest, with some of the stiffness of veneers in particular quite dramatically higher than we currently get out of radiata. Following on from this, we have a further research project around the peeling of durable eucalypts for laminated veneer lumber, presented by Clemens Alterner from the University of Canterbury. The durable eucalypts, while they also have natural durability, the stiffness that these products bring, while bringing some processing challenges, also brings some opportunities for markets not currently accessible. Following Clemens, we have Rosie back on deck to talk about cypress sawn products from young stands. Opportunities for early to mid-rotation products offer real benefit and return on investment to the forest owner. And then finishing out today's session is a presentation from Ming Hao Lee from the University of Canterbury around Douglas fir cross-laminated timber. I'm sure you'll find this very interesting, and Ming Hao has been doing a lot of work on the fixings, etc. with CLT as well. Just a reminder that there will be the opportunity to ask questions at the end of the presentations, of which I'm sure you will fully enjoy. Thanks.
Good morning.
My name is Florian Greichen. I'm one of Scion's new general managers, and I'm here to talk to you about options for new high-value wood products. Well, how do you kick off a webinar-type conference? A talk like Options for Higher Value Wood Products has a very, let's say, transactional sound to it. The title is correct, the title is appropriate, but let me try something different, something that reflects how we feel about forests and something that is closer to our heart. Let's talk about all the product opportunities that come from forests. Let's talk about things that are not necessarily identifiable as products in the traditional sense, but these are so important. So in very simple words, let's talk about why we love forests. So in the next 10 minutes, I will take you on a discovery journey. I will be exploring reasons why we love forests. So let's get started by talking about the global challenges of the 21st century. They are internationally, but they also apply to New Zealand. We need solutions, and an opportunity is transitioning to a circular bioeconomy. Let's also talk about connecting forests with products we know about, but also products we have not identified as such. And finally, why should we be doing all this now? So what are these big global challenges that will shape the 21st century? Well, we need energy, but it has to be decarbonized. Our materials need to come from sustainable resources, and we must safeguard biodiversity. It's about restoring and enhancing it. Climate change. This is probably the biggest challenge of our generation. Land use. How do we relieve pressure on our land? Resource scarcity. We are consuming as we have a second planet available. Food loss and waste. So how can we feed 10 billion people in 2050? The demographic change. How do we address an aging and growing population? And finally, technology. How do we use the flood of technology advances, but how do we use them for good? So the linear economy of today is not an answer. The answer to all these challenges can only come from transitioning to a circular bioeconomy. And forests are at the heart of this transition. The circular bioeconomy offers absolutely game-changing solutions. So this type of economy enables a carbon neutral, renewable and exclusive economy. And overall, it's a society that prospers in harmony with, not against nature. So this economy uses renewable natural capital to transform and manage our land, our food, our health, our industrial systems, and all with the goal of achieving overarching sustainable well-being. So with these principles of a circular bioeconomy in mind, here are 5 reasons why we love forests. So forests are at the heart of unlocking significant GDP growth for our country if we move beyond business as usual. So this graph shows 2 scenarios for the forest sector GDP contribution up to 2050. So the business as usual prediction, and that's here shown in green and light green, this is considering traditional logging, wood, paper opportunities, will only give a moderate increase in GDP by 2050. But then looking into 2050, we can also see a different future. A future where the contribution could be about 10 times larger in numbers. So this future includes onshore manufacture of new high-value forest-based products, So this could be biochemicals, bioplastics, biofuels, higher value wood products. All this manufacture and all this value add will happen somewhere in the world. And we have the chance to make it happen in New Zealand. A circular bioeconomy is about economic growth, but with nature, not against it. So forests are at the heart of improving our environmental footprint in critical areas such as soil health, erosion control, air quality, carbon sequestration, water quality, biodiversity, and general well-being. And it's really important that all these contributions should be seen as products. Forests are absolutely critical for New Zealand's journey to zero carbon. So they're offering opportunities for carbon sequestration, but also renewable feedstock for bioenergy, the bioplastics, all the material we talked about. And they are alternatives to currently really emission-heavy materials, products, and processes. Also, how we build our houses, our buildings, has a significant impact on how we respond to climate change. Less steel, less concrete, more wood, all this could significantly help New Zealand to hit our carbon targets. Science and innovation are the key enablers of a strong Maori economy in the future, and forestry and forest-derived products will be a cornerstone of this economy. So this is a great, unique New Zealand opportunity and absolutely not to be missed. So given the close link to feedstock, the circular bioeconomy is a key contributor to economic growth in rural areas. So it is an engine for sustainable development in rural and regional New Zealand. So this type of economy offers innovative solutions to generate wealth, generate jobs, generate environmental benefits, all from this global opportunity. But the opportunity is to capture all these benefits in our regions. Well, that might sound very ambitious, and it is very ambitious. And these are our ambitions for New Zealand. We can only achieve them in partnerships. And we are very bold in claiming that forests are the resource that will get us to these ambitions and to this future. So for us, it is all about how we value and use forests. It's directly or indirectly. It is to enrich our country, our communities, and ourselves. So in this 2050 future, so we envisage forests as a highly regarded renewable resource, a resource that is absolutely pivotal to New Zealand's economic, environmental, and social well-being. Well, the final question is, why now? Well, the stars are aligned, and New Zealand has always responded very well to change and challenges. So the world as it is at the moment is changing at a much faster pace than during the Industrial Revolution about 200 years ago. This change is coming like a tidal wave, and it will sweep away the old economy. So the choice at the moment is ours. The time for all this change is right now. So the opportunities you have is you fight the change and hold on to an old economy, or are we working towards a future, and a future that would mean our children and their children are enjoying living standards far superior from what we can see today. So forests are at the forefront and are the foundation for this aspirational future. We can't get there without forests. And for all these reasons that I've just given you, for all these reasons, this is why we love forests. So I hope I was able to take you on a very exciting journey. I think there's great opportunities, great future ahead of us. And I wish you a very enjoyable and very fruitful conference. Thank you very much.
Morena, I'm Warren Grigsby. I'm a research leader here in Rotorua, and I'm also the science program leader for an MBI funded program to develop a New Zealand bark biorefinery platform based around bark. So it's a 5-year endeavour research program, and our brief is to develop applications and integrate new extraction technologies to unlock the hidden value of New Zealand pine bark. It's just over $2 million per annum over that 5-year period, and our focus is to develop new co-products and applications for bark. And key for this is developing and ensuring we have industry partnerships in place. It's a good example of the circular economy in action. So very briefly, Bark 101. More than 90% of New Zealand's forestry estate is radiata pine. There's an advantage there that it's a single bark species. So when you come to collect the bark, it's all the same compared to some of the other forests that we have around the world. Bark protects with unique attributes, and we want to unlock some of those attributes from the bark. So there's antioxidant activity, UV absorbing activities, antimicrobial, and bark has a waterproofing role as well. Bark contributes around about 5% of the tree mass, and as we know, not all bark is created equal. There's physiological differences, chemical differences, and you see that in the stem bark, where you go from chunky bark at the bottom of the tree to stringy bark at the very top of the tree. In New Zealand, there's lots of opportunities to capture bark and create value or from volume of that bark. Currently, a lot of the bark is lost during harvest and log recovery, but you can see from some of these numbers, there's still a lot of bark on a green tonne basis available in different places that we can access. So valuing bark, it really is an opportunity. Currently valued at around about $25 a green tonne. With some of our techno-economic analysis, we can see that we can lift that tonne of green bark to $200 based on extracting tannin from the bark and doing solid fuel applications such as briquettes. And in our second generation, the work that we're trying to deliver in our program, we value that green tonne of bark at up to $6,000, where we've got a suite of different co-products which leverage new technology, new co-products and new markets, both here domestically but also export. So our concept for the bark biorefinery is to take logs, debark these before they go on for onshore processing or for export. That bark can be sequentially extracted to give us extraction products. Example of that currently is tannin, but we're also looking to extract suberins and also pharma and bioactives. Further on in our biorefinery, we can hydrolyze and ferment through biotechnology applications, delivering biofuels or bioplastics, and then of course encompassing circular economy. Even within a bark biorefinery, we can take the solid residues, process those into briquettes and pellets for energy, or taking those through to growing media and into animal feeds and advanced applications. So that bark composition is very different to what you see in a tree. You see a lot of tannins in the bark. They're the ones responsible for antioxidant activity, UV absorbing properties, and also antimicrobial and antifungal activities. Suberins also make up a large proportion of bark. They're the hydrophobic components responsible for waterproofing the tree, keeping water inside, but equally water outside the tree. So if we consider the sustainability of using a whole bark in a process, we can create some value. So in our Generation 1 bark biorefinery using existing technologies, we see applications in energy and tannin products. Tannin is currently retailing for $1,500 to $3,000 a tonne, so you can already see potential applications in adhesives and leather tanning, both here on shore in New Zealand, but also export opportunities for tannin products. We also see solid fuel applications through briquetting and pellets. In our Generation 2, which is really the heart of our program, we're looking to develop new chemical and polymer co-products and also develop markets for those internationally. So when we go around in our full circle, we see that we can take bioactives and farmers as very high value extractives from bark. We can also utilize second generation tannin and flavonoids in resins, plastics as additives for protection roles, particularly around UV protection and antioxidant activities. We can still use the bulk tannins and industrial chemicals. We can take some of our fermentation residues into biotechnology processing. We can take the suberins into waterproofing and coating applications. Again, very high value applications. We're looking at thousands of dollars per kg, and we can also deliver those hydrophobic materials into polymer systems with energy and solid fuel applications for the residues. Some early stage progress that we're doing. We've already moved from lab to pilot scale to commercial scale supercritical carbon dioxide extractions of bark, progressing from kilograms through to tons. So we've already done a ton scale trial extracting bark waxes, where the yields from the bark are typically around about 5% for those bark waxes. Those bark waxes can be used as natural water repellents, and we've got some examples coming through where we're using these in paper, textile, and leather coatings as water repellents. And lastly, we talked about the connectivity and partnerships being important for us. You can see through our activities, both in Generation 1 and program developments in our Generation 2, we have a number of partners, both here in New Zealand, in terms of industry, as well as academic research institutes contributing to the program and a vehicle for driving ultimately implementation of our bark biorefinery. With that, I'd like to conclude and look forward to your questions and question time.
The time to stop runaway global warming is running out. Fast-growing forest trees are the most effective way at this time for us to fight climate change. They suck carbon from the atmosphere. That's a big environment plus, and there's more jobs and income if you grow trees than farming sheep and beef. That's why so many smart farmers are so bullish, planting out trees and loving our forests.
Hi, I'm Rosie Sargent from the Wood and Fibre team at Scion, and today I'm presenting about some work we've been doing in the thermal modification area. So thermal modification is a process where we heat the wood to high temperatures in the absence of oxygen, and this prevents the wood from burning during the process. And this changes the chemistry of the wood cell walls itself without having to add any chemicals or anything else to the wood. So down bottom right here, we've got a little diagram of, simplified diagram of the polymers in the wood cell wall. Hemicelluloses have these hydroxyl groups on them which bond to water, and the thermal modification process removes some of those hydroxyl groups, so we get less water associated with the wood. And this has a number of changes to the properties of the wood. So with severe modifications, it increases the durability of the wood and it increases the dimensional stability, which means that the wood shrinks and swells less in response to changes in moisture content. It also darkens the wood colour, as you can see from the picture here, and for severe modifications it can reduce the strength of the timber as well. So thermal modification has been commercialised around the world for quite a large number of wood species. In New Zealand, radiata pine, thermally modified radiata pine cladding is sold. So we are now looking at other New Zealand grown species that we could thermally modify with the aim of increasing the sapwood durability, but also boosting the durability of the heartwood of species that already have a little bit of durability in the heartwood. So for this, we chose Douglas fir and Cypressus lusitanica. So here is what the two species look like before they have been modified. And then we modified them at 220 degrees. You can see they've gone quite a lot darker. And then for the Douglas fir, we did an even higher temperature, which is darker again. And these sort of temperatures are similar to what the commercially produced radiata pine is in New Zealand. So the primary property we are looking for here is improved durability. So in New Zealand, a product like, say, a deck has a minimum service life of 15 years, but we don't want to have to wait 15 years to see whether a modification worked or not. So we have a range of durability tests that we can do, accelerated tests, starting with a lab test where you use very controlled conditions. You can get a result in a matter of months, but it only gives you a very broad indication of whether you've got increases in durability or not. Then going on to Fungicella stakelets. So this is where we have a warmed bed of soil and we have like little ice block sticks from each wood type, and this runs for a number of years, typically around 3 years. And then you go on to outdoor durability tests, which better mimic in-service conditions. So this is like mimicking a cladding application, but it's more severe than you would get in cladding in a house. So you can get a result in, say, 7 years. And at the moment, we are about halfway through the Fungicella stakelet testing for these two species. So for the Fungicella stakelets, for each wood type, we have roughly 10 samples, and every 3 months they will get removed from the soil and they get assessed for their condition. So a condition of 10 means that they look absolutely perfect, and a condition of 0 means that they've rotted away completely. So the lines here, each point is the average condition for each of those 10 stakelets, and then the error bars show one standard error. So there's actually quite a lot of variation in condition between stakelets within the same wood type. So the light blue line here, light blue lines here, is the unmodified Douglas fir. This is the condition is dropping off relatively rapidly. That's not surprising. Douglas fir heartwood does have a bit of durability, but not a lot. So it's not really a surprising result that it's performing similarly to sapwood. The darker blue lines are the modified Douglas fir, and you can see that there's a big increase in the condition of the stakelets, showing that we likely have an increase in durability We also have a number of control samples that we include in these tests of materials that we have a good idea of how they're going to behave. So at the top line, we've got CCA treated radiated pine. We expect this to perform well above the minimum required for decking in New Zealand, say. So we'd expect that to have a very high condition and do well. We have Tōtara heartwood. Tōtara is a class 1 naturally durable species. That's the highest durability class. So again, we would expect that to be performing very well in this test. And then we have thermally modified radiated pine, which has been approved for use as a cladding product. And we would expect that to be towards the lower end of the minimum requirements for outdoor use in New Zealand. So both the thermally modified Douglas fir heartwood and sapwood are not significantly different to the thermally modified radiata and the Tōtara. And the thermally modified sapwood is not significantly different to the CCA treated radiata pine as well. So this is a good result, shows we're getting broadly similar behaviour between our thermally modified samples and the controls, so it is worthwhile going on to downstream testing. And then again for the Lusitanica, the sapwood, the pink dotted line, unmodified, that drops off relatively quickly, which is not surprising. The sapwood isn't durable. The heartwood, solid pink line, is all of the stakelets are in a better condition. That's not surprising. Lusitanica is in the upper end of class 3 natural durability, so it has a degree of natural durability. And then after the modification, the red lines, you can see both the heartwood and the sapwood. There's this really big jump in the condition of the stakelets. So, and they are not significantly different in condition to all of our controls. So that's a really good result, and that's a really strong indication that they're performing similarly to these other materials, and it's worth going on to longer term testing. So where to next for this? The Fungicella stakelet tests, we're going to continue testing until all of the stakelets have failed. So for some of those more durable samples, that might be quite a long time. And in the next few months, we're going to be installing outdoor durability tests. So flat panel tests, which sort of mimic a cladding application. It's a north-facing frame at 45 degrees, and the samples sit on these rails that are made of untreated radiated pine. So the idea is that these rails will get fungi living in them, they'll start to decay, and that will make sure that decay fungi are introduced to all of the samples we're testing and potentially make them rot faster. And then we have decking tests where, again, you can see the deck is very, very close to the ground. It's got grass growing through it. It's quite a severe test, so you're expecting to have a shorter service life or shorter life than you would have for a standard deck, so you can get some results sooner. And there's a big team of people who are working on this with me, so I would like to thank them all for their contributions, and thank you for listening.
Our planted forest industry, challenging to be our second primary export earner. Woods, environmentally good in plant and product for building and landscapes. We're great in technology and science, selecting stronger, straighter trees, safer ways to harvest them, cleaner and earthquake-resistant ways to build. Forests, regionally vital for economic development, creating all sorts of jobs. A prime future investment for our nation. Love our forests.
Hello, my name is Rosie Sargent. I'm from Scion, and today I'm presenting about producing veneer and sawn timber from Eucalyptus fastigata. So the major aim of this project was to try and produce veneers for making sawn plywood or laminated veneer lumber that had a higher average stiffness than you can get from radiata pine grown in New Zealand. And eucalypts tend to have stiffer timber than radiata pine, so we decided to look at Eucalyptus fastigata. Additionally, a lot of work that has been done on processing eucalypt around the world focuses on pulp regime logs, so young trees and stands that have not been pruned and have not been thinned. So here we decided to look at a stand that had been produced specifically for high value saw logs. So it had been high pruned, thinned, and the trees were a bit older. We wanted to understand processing issues around processing these eucalypts. So you get growth stress where the center of the tree is in compression and the outside of the tree, the wood, is in tension. And once you start processing that, you can get splitting in the ends of the logs, and if you're cutting boards off the logs, they can bend and distort. And also, if you're producing veneer, you want to make sure that you can actually glue it together and make it into things. So just a little bit about the trees. We found a small stand of 24-year-old fastigata trees in Marlborough. There's a little aerial photo there. And we got a pre-harvest inventory done where every tree was assessed. We then also measured the acoustic velocity and drilled them for a resi trace for a subset of the trees. And then 20 trees from the stand were harvested for this trial. The logs were graded specifically for the requirements for this trial. So the peeling and the sawing was happening at J&L in Wairarapa. And obviously for peeler logs, the logs need to be very round, the logs need to be very straight. And also in the sawmill, they produce high value appearance grade radiata pine for export. So they have quite tight restrictions about around their saw logs as well. So anything that didn't fit our specifications for this trial was graded as firewood, essentially. So that meant that we had quite a high proportion of out-of-spec logs, around 35% of the total recoverable volume. This also wasn't helped that during the harvesting, one of the trees split from end to end while it was being felled, which meant that several nice peeler logs ended up in the firewood bin. So producing the veneer, the logs got put on the ferry and sent to Wairarapa, and just over half of them were suitable for peeling. The main reason that they weren't suitable for peeling was if they had significant end splits in them. So you can see down on the bottom left, that log there, if you were to peel that into veneer, you would end up with some pretty ragged veneer sheets. The logs to be peeled were sorted into 3 stiffness groups. This was to see if we could use log segregation to try and really target the stiff veneers that we were trying to produce. And the peeling itself went pretty smoothly, and we ended up with 60% recovery from the peelable volume through to trimmed dried veneers. So we were quite pleased with that. So the main property we wanted to understand with the veneers was the stiffness. So the black lines in the histogram there is data from some typical production at the mill, and then the coloured bars are our 3 stiffness groups of logs. And you can see that even the lowest stiffness group of logs, we've got a significantly higher average stiffness compared to the typical radiata pine. And then that stiffness just keeps increasing with the higher stiffness log classes. So that's a really positive result. There was a potential issue with end splits in the veneers. Unfortunately, we don't know when this end splitting occurred in the process. Normally there will be a camera doing automatic visual grading of every veneer as it comes out of the dryer in the mill. Unfortunately, it wasn't working during our trial, so we didn't get that information of how many splits there were in the veneers immediately after they'd been dried. And once we got them here to Rotorua to do other measurements on them, they had been handled numerous times, and it's very difficult to handle veneers without damaging them. So that's a bit of a gap in our data. So now we have all of this veneer. Next step is to try and make some LVL out of it to confirm these properties that we've been measuring. So all of the logs that were not suitable for peeling, J&L offered to saw them into timber for us. Now, because the main reason that logs weren't suitable for peeling was because they had end splits, we were essentially choosing the logs with the highest levels of growth stress to saw. So we would expect to be seeing growth stress related issues with the sawn timber. Additionally, we were using a radiata pine sawmill that is not optimized for species with growth stress, and we didn't make any effort to try and change the way the sawmill was operating to be able to mitigate the effects of the growth stress. So the result of that was we got a relatively low green recovery of green sawn timber out of our logs. So wood was then sent to Rotorua and we air dried it. We got quite a lot of cell collapse where the wood just basically shrinks in on itself during the air drying, but the boards were then steamed and had a final kiln dry, and that recovered most of the collapse. So the sawn boards were then graded, and the main reasons for them being degraded, so box grade, essentially reject grade, the main reason for being degraded down to box was because they had crook. So that's distortion where the board basically bends sideways. We had around 10% of the boards in a clears grade, and then had a high feature flooring grade, that's an Australian grade, which allows some small knots, resin streaks and features, and then cuttings grade, where you're essentially cutting it into shorter lengths, so for finger jointing. The second most common defect we got were gum veins or kino, where a lot of the boards had either pockets or these bands of dark brown gum, and you can appreciate that a board like that can't really be classed as clears grade because it has large streaks all over it. So the key results from this work, the veneer stiffness we got was significantly higher than radiata pine. Generally the veneers peeled well, but there is this possible issue with end splitting that we weren't able to get to the bottom of. The sawing process was not optimized for growth stress, and it really needs to be if you want to get a decent amount of good quality timber out of it. And we need to find a way of reducing the distortion in the sawn timber, and it may be that improving the sawing would help with that. And another key take-home message for us is that you need to have a market for every single log. No, you can't just take the very best logs like we did and downgrade everything else to firewood, because then you are throwing away quite a lot of your resource.
Hello, I'm Clemens Altana from the School of Forestry at the University of Canterbury, and I'm working on durable eucalypts together with the New Zealand Dryland Forest Initiative and ZDFI. The topic of my talk is durable eucalypts for LVL, laminated veneer lumber. And if we look at New Zealand, it has an existing LVL industry based on radiata pine, and there are 3 places where it is made. And LVL is a structural product, so its value is determined by its mechanical properties, and the way an indicator for that is the modulus of elasticity, or the stiffness of the product. And we can see that the products manufactured in New Zealand are between 8 and 13 gigapascal in stiffness. And if we look outside of New Zealand, internationally, there are stiffer LVL products available up to close to 17 gigapascals, and it is twice as stiff as the New Zealand LVL products. Now, 17 gigapascals, that is what timber engineers say it's comparable to steel, and they can use such high stiffness engineered wood products to construct really tall wooden buildings. And this is a picture of a study from Sumitomo out of Japan, designing a 350-meter tall all wooden skyscraper. And it cannot be made from lower grade LVL, but they need high stiffness engineered wood products to achieve that. Okay, so why can other people make this high stiffness LVL and we in New Zealand don't produce it? And it has to do with the wood which we have available, which we use to make the LVL out. We make it out of radiata pine, and if you look at solid timber, New Zealand grown radiata pine, in average it has a stiffness of 8 gigapascals, but there's some wood which is stiffer, and there's also wood which is less stiff. Now, if you look on the LVL products, the average stiffness is higher, let's say 10 gigapascals. And how can that be? It is achieved by creaming up the stiffest logs and the stiffest parts of the logs and converting it into veneers and using it for LVL production. Now, the data comes from a study from Doug Gaunt at Zion. And in this study, they actually looked at using Eucalyptus nitens for LVL production. And they have shown that you can make a really nice LVL product out of Eucalyptus nitens with an average stiffness of at least 14 gigapascals. So now we know how it's technically possible to achieve that. It's by using other wood. And while we have a resource of a smallish resource of non-durable eucalypts like Eucalyptus nitens, fastigata, and regnans, I particularly work with NZDFI on ground durable species, Bosistuana, quadrangulata, and Globodia. And while they have not really been chosen for their mechanical performance, but for their ground durability, it happens to be that they also produce very stiff and strong wood, more than 20 gigapascal in stiffness, and therefore they are really good starting place, a good material to start making LVL out of it. So while we now have a technical solution to it, to the problem of how to make stiff LVL, we asked the question, is it also an economically viable proposition? Is there a business case for them? And the way we approach this is looking at all the variation which we have in trees, in terms of shape, in terms of stiffness, and what we know about Eucalyptus bosistuana, and then see how these individual factors of shape, of stiffness, of shrinkage affect the value of a tree when it is converted into into veneers for LVL protection. We know the value of the veneers, and we also know the properties of the trees, so we can figure out what's the sensitivity of the value of different factors. So we looked at volumetric shrinkage, stiffness, geometry of the logs, the amount of usable veneer which we can get out of the trees, and then a lot of different ways how we can convert the logs into veneers, different peeling technology. And to figure out the sensitivity, we compared a bad case with a good case. And while there are some variables which don't affect the value of the trees at all, we are not really caring about it. The single most important one is the amount of usable veneer which we can get out of the logs. So what do I mean with usable veneer yields? I mean what is visualized here. So we actually have taken some of the durable eucalypts to a LVL plant, peeled them into veneers, and from some logs we get really nice veneers out of, and also in good yields. But there are some logs in there where we hardly get any veneer out, and the veneer we get out is full of these cracks at the end. And these cracks are a direct consequence of growth stresses in the trees. And growth stresses are really the single most important factor preventing eucalypts from being used in solid wood products. And this is affecting hugely the yield for the eucalypts. Now, we also know that there's a solution to that, because growth stresses are variable, so there are good logs in there with low growth stresses. We know that they are under genetic control, and we have a means of measuring them really quickly in a breeding program. So we can reduce the growth stresses, we can increase the yield of usable veneer in the peeling process with planting better genetic stock. And we have assessed species of the Dryland Forest Initiative for low growth stress, and these plants will now be available for planting. I also want to mention that this problem of growth stresses and end splitting in the veneers is not unique for the durable eucalypts. It also applies for Eucalyptus vastigata and nitens, the non-durable species of which we have a small forest estate here in New Zealand, but they have not been screened for growth stresses yet. Okay, now we know the problem, but we also know the value of the trees, and we also know the growing costs of Eucalyptus bozestoana trees, depending on the growth rate on the site and depending on planting subsidies. The growing cost for Eucalyptus bozestoana tree to get it to 30 centimeters DBH is between $20 and $56 per tree, and that already includes an internal rate of return of 8% to the forest grower. So if we can sell it at that price, the forest grower makes a profit. Now the value of those trees, depending on the wood properties, depending on the technology we use for peeling, is exceeding that. So even in the worst case scenarios, the value of the trees is exceeding the growing costs. So this margin, which is between there, needs to cover not only the profit for the manufacturers, but it also needs to cover harvesting costs and transport costs and production costs. So now it's up to the LVL manufacturer to see if this margin is actually big enough for them to also make a profit. So there is a business case for planting those trees out. The trees are becoming now available, and there's lots of research going on in the space of durable eucalypts with postgraduate students here at the School of Forestry, a larger team of researchers in the NZDFI, and a lot of support from the government and the industry to undertake this work. Thanks for watching, and I hope to see you soon in person.
Hello, I'm Rosie Sargent from Scion, and I will be presenting today about some work we've been doing producing sawn timber from young cypress trees. So in 1997, Scion established a cypress hybrid trial, which included a number of new cypress clones. And these trees are now becoming large enough that we can use them for processing studies, like seeing what sort of sawn timber we can get from them. Another aim of this work was to see what sort of sawn timber recoveries we can get from relatively young trees that have not been pruned and have not been thinned, so a relatively low cost silvicultural regime. And Dean Satchell from the New Zealand Farm Forestry Association was quite heavily involved in this work, and he had a new sawing strategy that he wanted to test for these cypresses to try and maximize the recovery of wide boards with a high grade. So the two clones we were looking at was GH5, which is a Cypressus lusitanica, and Avenzii, which is a hybrid. And we got 8 trees of the lusitanica and 6 of the Avenzii. You can see the lusitanica trees were a little bit larger, but they had a little bit more sweep to them. So the sawing was done at Ruapehu Sawmill in Ratahi. They do a lot of cypress sawing, so it was an ideal site for us to use. When we do sawing studies at Scion, we tend to apply sheets of barcodes to the ends of our logs. You can see them in the picture here, and they stay attached to the boards after the sawing, and it means we can track each individual board back to the tree it came from and to the position in the tree, which is really useful. Normally, say when you're sawing radiata pine, typically if the logs have a lot of sweep, you would have the ends of the logs pointing up or pointing down, sometimes called horns up or horns down. Here we had the logs on their side on the saw carriage because we had this resawing technique to try and mitigate the effect of the sweep while still getting quite wide boards out of the logs. And so yeah, the main objective was seeing if we could get these large recovery of wider boards out of these logs. So each log was cut into flitches. Most of them were 25mm thick, but we did cut some at 30 or 50mm thick, and the sawing went very well without any problems with cracking or growth stress or any of the issues we've had with sawing eucalypts. So log gets sawn into flitches, then it gets flipped over and then sawn all the way through. Then these flitches get docked into 2 pieces, not necessarily docked in half. The point that they're docked at gets chosen in order to maximize the recovery of timber you would get out of each half. So if you have a flitch with a lot of sweep in it, like this top one, if you cut it in the middle, you end up with 2 straighter flitches that you can then resaw. Or if you have a lot of taper and say some large defects, you can cut to minimize the impact of that. And so then once they've been cross-cut, these flitches were edged in a twin blade edger, and you can see the green outlines in the diagram at the bottom shows how you're able to get wider boards out of these 2 halves than you would if you were able just edging the entire flitch. So from this we got quite a high green recovery, so 58% of the volume of logs that went in we got back out as sawn timber, so that was a really good result. The boards were then fillet stacked and air dried in Ratahi down to around 16% moisture content, and then we got them transported to Scion to be graded. The quality of the timber after drying was very good. We didn't really see any evidence of drying defects like surface checking. We didn't see any signs of collapse. Previously I have seen cell collapse when drying lusitanica, so it was good to see that we didn't have any here. So the grading, we graded to a range of appearance grades. We didn't have a clears grade. Every single board had knots in it. So we had what we called a cladding grade. This is similar to the dressing grade in the New Zealand grading standards, but has tighter specifications around knots, for example, and this is intended as timber you would use for a cypress weatherboard, which is quite a common high value application for cypress sawn timber in New Zealand. Then we had merchantable grade and then box grade, which is essentially reject. Then number one framing, so a visual structural grade. And for the larger boards, we also measured the acoustic stiffness. And I should note that when we were doing the grading, often before you grade timber, you would dock any damage off the ends of the boards, potentially resaw them to a different width if there are defects on the side of the boards. We graded the boards as if that had happened, but we didn't actually do that. So the graded volume for each board was generally a bit smaller than the volume of the board itself, because we assumed that things would have been cut off them. And the barcodes are still attached to the boards, so we're able to track this grade information back to each individual log. And once we have finished this work, this graded timber will be available for other projects. So we're going to be looking at the durability of the Avenzii. Being a relatively new hybrid, we don't have a lot of information about how it performs. And we're going to be looking at characteristic stresses. So this is bending properties of full-size boards, which is required for standards, and also looking at mechanical properties of small clear samples that are cut from different positions in the trees. So some very high-level results from the grading. The grading was only finished very recently, and we haven't finished analysing the data. So we got 51% recovery of dry graded timber from the volume of logs that went into the process. So we're pretty pleased with that. And the recovery of our two highest grades, which was the cladding grade and the number one framing, were very, very high. So every board had a length in it that would meet the number one framing requirements, and more than 90% of the boards met the cladding grade. It should be noted that if you were to use this for cladding in New Zealand, the boards would need to be either resawn to remove sapwood from the edges, or you would have to use some other process like, say, thermal modification to increase the durability of the sapwood. So being young trees, we have quite a high proportion of sapwood in these boards. So it's only 30% heartwood, say, for the Lusitanica, but much higher at 55% for the Avenzii. And the boards that were downgraded to merchantable grade or box grade, the main reason for that was that they had bark encased knots. And I'd like to acknowledge all of the people who helped me with this work. There's always a large team of people behind these projects, and I would like to thank you for listening.
Good morning, everyone. Thanks for coming to my presentation. This morning, I'm going to give you a brief update on experimental research on Douglas fir CLT for mass timber construction. As we know, CLT is now being widely used in New Zealand, Australia, and globally. It provides versatility and sustainability for building industry. Unfortunately, as a relatively new engineered timber product, CLT is not covered by the current New Zealand Timber Design Standard 3603. And also the forthcoming New Zealand standard does not cover CLT design. Therefore, there's a need to provide technical evidence to specify New Zealand-made Douglas fir CLT into future timber design standard so that engineers will have confidence to specify this type of product. And also another great benefit really is to add values to Douglas fir timber's resource in New Zealand by specifying and providing technical solutions of using Douglas fir CLT for multi-story building design. My talk will briefly cover 5 parts, so I will give you a quick introduction of the current trend of building tall timber buildings, and then move on. We are looking at different testings to evaluate rolling shear strength, to understand the critical connection behavior in Douglas fir CLT, and also to develop a low damage CLT wall system to resist earthquake load. And then last, I will talk about some conclusions. So a lot of people say CLT is a type of jumbo plywood, but the difference is plywood using thin veneers. In CLT, we use much thicker timber lamination, typically structured timber boards, and they laid up together in a crosswise way, and then we also apply adhesive on the wider surface so that they can glue and bound together. And at the same time, we need to apply pressure to cool the adhesive. So on the right side, I want to show this a Douglas fir CLT panel with really a large size, 2 meter wide roughly, up to almost 6 or 7 meter long. So this is made the New Zealand Douglas fir CLT, and you also notice that there are a number of cavities. We leave these cavities by leaving some boards during the manufacturing process. So the cavities are used to run post-tensioning tendons, steel tendons, to anchor the wall into the foundation. These 3 buildings are recently built. These are really one of those tallest timber buildings around the world, 18-story, 24-story, and 13-story. All these buildings used CLT as major structural elements. So particularly in these 13-story building, so it's 100% CLT buildings with glulam as the main structural components. So pure timber building, and the other 2 is kind of a hybrid CLT with concrete, etc. So coming to New Zealand and Australia, we've built quite a few CLT buildings. So for Tay Building on the left side is one of the earliest CLT construction in Australia and around the world. 10-story, 9-story CLT construction sitting on 1-story concrete podium, and 25 King, another timber building using CLT floor system. And on the right side, we've seen 2 multi-story buildings for residential application. So they all used New Zealand-made CLT products. I mentioned CLT is similar to plywood, having wood fibers oriented crosswisely, and in actual application, we have to be careful about rolling shear properties of CLT because sometimes it may govern the capacity of these panels. So we did some bending test and planar shear test really to derive the design strength for rolling shear for Douglas fir CLT. So our testing results indicate roughly 1 megapascal as the characteristic rolling shear strength, so that engineers can specify these value in the CLT design, in the Douglas fir CLT design. As I said, connection components are critical components in timber buildings, particularly under earthquake load. Connection behavior essentially governs the building behavior, because we know wood is a relatively brittle material, so under earthquake load, it is not able to dissipate much energy. So essentially connections are the source of energy dissipation for most of timber buildings. Therefore, in New Zealand, to design buildings, timber buildings, to resist high earthquake load, it is very critical to understand connections with a different type of fasteners, fixing types. So the first connection test we did is on the hold-on connections using big size dowels. So these hold-ons are critical component for a CLT wall to resist earthquake load. Imagine without this proper design of hold-ons, these walls are not able to resist any earthquake load or wind load, because these walls can be tipped over very easily. So in our lab, we tested different thickness of CLT panels, different sizes of dowels. The main purpose is to derive these load displacement relationships and to understand strength and stiffness, understand energy dissipation, and also we try to improve the connection details to achieve better connection behavior. We also looked at commercial hold-on design using these commercial hold-on brackets. So these type of hold-ons are not as strong as the previous dowel hold-downs, but they are cost-effective and they can be used efficiently for relatively low CLT structures. So this purpose, again, this test is to look at ductility and overstrength and provide information for design engineers to design wall structures using these type of hold-on devices. And the third part of the connection test is on the self-tapping screws. Okay, so we are looking at these proprietary product commonly used for mass timber construction. Most of them are European product, and their design document or equations are mainly derived from European CLT product using different species than the species in New Zealand. Therefore, this testing is to really verify those design equations and try to check those design parameters, see if they are also applicable to New Zealand Douglas fir CLT. And then we move on to look at connection behavior using these long self-tapping screws. Again, we tried to improve the connection details to design stronger and stiffer screwed connections to connect these CLT panels in orthogonal directions. The last connection testing is on the conventional wood-to-wood carpentry joints. So without using any mechanical fasteners or steel plate, we try to understand the shear capacities of these carpentry joints. And we know we can follow some design equations to predict these castellated or carpentry wood-wood connection. However, we noticed that some design equations are okay in predicting the actual strength of the joint. However, in some circumstances, the predicted equations are very conservative, and we think there's a room we can improve the accuracy of those prediction equations to predict the shear capacity of these castellated joints. And Wall testing project, we put a lot of effort to test large-scale single walls, coupled walls, and flanged core walls. So the single wall and the coupled wall are typical wall setup in CLT construction, but the difference in our testing is we introduced a post-tension tendons going through the entire height of these walls, and these tendons will be applied with high post-tension forces. Therefore, it can bring these walls back under earthquake loading. So then we introduce additional connection types to dissipate energy. Therefore, we can really concentrate seismic damage in local area. And after big earthquakes, we can go do quick inspection and replace those damaged connections, for example. So on the right side, this gigantic bookshelf essentially is trying to simulate the lift shaft designed as critical core wall structures to resist lateral load. And we believe by having these returning walls incorporated into a shear wall design, we can significantly improve the strength and the stiffness compared with the single walls and coupled walls. And our testing result proved our concept of introducing these returning walls as part of the shear wall structure. So I'm gonna give you a quick video showing the last test phase on these core wall structures. We simulate earthquake loading on top of the wall by applying the forces along two orthogonal directions, and we basically track the amount of load and the amount of displacement, and then we derive the wall strength and stiffness and energy dissipation and ductility, etc. So these walls have been tested in many sequences of loading, and it performed very well, and we observed only local damage at the base of the wall, and we believe those damages should be easy to repair. And these are some connection details. We basically tried the different orthogonal joints between the vertical wall panels. And the last case, we showed the best performance by having these screws installed in different angles. And we believe we've achieved significant amount of composite actions. And that's why these walls behave much stiffer and stronger than the other cases. Here are some quick conclusions. And from our testing, we found Douglas fir CLT provide superior structural performance for multi-story building application compared with light timber frame construction. And robust and ductile connection detail can be achieved in Douglas fir CLT to resist high earthquake load. And proper designed low damage Douglas fir CLT wall structure can significantly improve seismic resilience. And we believe these type of core wall structure offer a lot of more flexibility to CLT building design. And research is still ongoing currently. So we are looking at a different type of Douglas fir CLT connections and different wall solutions to really provide different solutions to improve the structural efficiency compared with conventional solutions. These are the sponsors we would like to acknowledge. And also I want to thank our research team, student Justin Brown, Wen Chen Dong, Benjamin Mormon, Thomas Wright, as well as a great support from the our technicians. So this is the last slide showing great teamwork after the core wall testing was done. So really, I want to thank the great contributions from the students and technicians. And we pretty much also enjoyed this research project funded by SWP and other project funders. I'm happy to take any questions if you have anything want to ask.